Good evening. Hello.
Good evening, sir.
Yes. Good evening. Welcome to this live interaction session. I hope that you watched this week's lecture and practiced the problems also.
Yes, sir.
Okay. Okay. Thank you. Uh, okay. So I will get started with the session. So yes. Yes. So I welcome you all to this live interaction session. The title of the course is Advanced Reinforced Concrete Design. This course is brought to you by NPTEL, and this course is being taught by Professor Surya Prakash of IIT Hyderabad. And presently, we are in the 11th live interaction session out of 12. So this is the penultimate live interaction session, and we will be having our final session in the next week. And this session is brought to you by this session is presented by me. My name is S. Lalit Sagar. I am a doctoral candidate and PMRF fellow in the Department of Civil Engineering at IIT Delhi. So I have around 15 questions planned for today. So broadly, this week we have looked at the topics of serviceability and bond. Okay, so under serviceability we have in module 9.1 we have the deflection, module 9.2 we have the calculation of crack width, and module 3 we have the bond or the development length. So I will just take 2 minutes in order to provide context to today's discussion on serviceability. So this is the course plan this advanced reinforced concrete design, and in week 1 we looked into the introduction, the aspects of reinforced concrete construction. Then in week 2 we looked into the material behavior, that is concrete and reinforcing steel. Um, and then in week 3 we discussed the durability aspects. In week 4 we studied the behavior of reinforced concrete members under pure axial loads, and in week 5, 6 and 7 we dedicated to the behavior of flexural members. We studied their behavior under flexural loading, then shear force, and also the torsional loading. Then in weeks 8 and 9 we dealt with the columns. I think yeah, no, 9 and up to week 10 we dealt with the columns, and presently we are in week 11 actually, where we are dealing with the serviceability aspects. So once a structure is being designed for corresponding to the uh, ultimate strength, then we evaluate the structure for serviceability, which is why today's discussion becomes important. And next week we are going to conclude the course for this year with the analysis and design of two-way slabs. Okay, so with that introduction, today there are very lengthy problems, as we did in the last week also. Like our session went up to 2.5 hours. So this week also I have three quite involved huge problems based on deflection, then calculation of crack width, and the calculation of development length. So if there are any questions, I invite you to ask me. If not, with your consent, we can go ahead with the discussion of question and answers.
Sir, actually, the syllabus is given for week 12.
Yeah, yeah, yes,
Footings, structure, shear wall,
yes, yes, yeah, yeah, yes, sir.
deep beams.
Yeah, let me just open it for you. So initially we had kept these special topics, but the corresponding lectures were not recorded last year, and this year also unfortunately the professor could not record that, so we'll be doing up to the 2 ways labs only.
So any material at least can you provide?
Yeah, sure, sir. Actually,
Lecture notes, lecture notes.
lecture notes, I will discuss with sir, because it takes actually quite a lot of effort. Lecture notes, I will see, I will discuss with him and I will let you know. But anyway,
Only 1 week is left, sir. Remaining is completed actually.
I mean, for the examination, sir, we cannot include. But after the course, like if you want to learn, then we can.
Yes, sir. For learning purpose only because it is given in the
Yes.
syllabus. And if
Yeah.
that also we learn, then the entire thing will be completed.
Yes. But for most of the topics, we are referring to Pillai and Menon. So yeah, you can. I mean, we can refer to that. And in addition to that, I will discuss with sir, and I will let you know if we can actually arrange for some lecture notes or something of that sort, some resources.
Okay, sir.
Yeah, thank you. So with that, we can start today's session. So okay, I hope that my screen is visible. Okay, so we are going to start the question. So the first question is based on the concept. It's a conceptual question. Which of the following parameters are evaluated under the limit state of serviceability? So there are 6 options. So kindly take 1 minute and let me know what would be the appropriate answers.
So bond strength and durability.
Okay, thank you. So which of these following parameters are evaluated under the limit state of serviceability? So there are 4 correct
Deflection crack.
A, D, E, F.
Okay, yeah. Thank you for the response. Okay, so I think we can go ahead with the answer. So yeah, as the participant rightly mentioned, the correct answer is option A, D, E and F. So as we can see in this particular slide, so limits state of serviceability is defined as the state of design beyond which a structural system loses its serviceability and cannot be operational for the actual service load that the structure is subjected to. So essentially the parameters that are evaluated under the limit state of serviceability are the deflection. So we are going to be dealing with deflection in today's class. So we have deflection, we have, and cracking also.
Sir, bond strength where it will come, sir? Then?
Yeah, sir,
Bond
bond
strength.
strength comes under the limit state of collapse. So if you notice, if you have seen the numericals also, when we are calculating the deflection and crack, we use the service moment. So we just consider M, but for the bond strength we consider mu, that is factored moment. So that is 1.5 m. So bond strength is considered under the limit state of collapse only. So that is why this module is this module pertains to the limit state of serviceability and bond strength, because bond strength does not come under the serviceability. So yes, so in addition to that, the durability, which we discussed in module 3, and vibration, they also come under the limit state of serviceability, whereas the parameters such as the strength, overturning, sliding and buckling, we usually do this for the footings and the retaining walls. So these parameters come under the limit state of collapse. Okay. So
The vibration is seismic.
no, like vibration comes under serviceability.
No, vibration is what vibration?
Vibration in the sense, let's say that you have installed some kind of a machinery. So because of that, that machinery induces some vibration. So let us say that there is a multi-story building. In dynamics also you might have seen problem like this, where there is probably a shear wall. Ideal is this multi-story building idealized as a shear wall, then you put some sort of a machine over here, okay, machine, and this you give it some sort of a vibration or a periodic motion, right? So then if what would be the deflection, right? You can consider this as x. So the deflection that is caused due to vibration, that is measured under the serviceability. Okay, so I think we can move on to the next question. So question 2, what should be the minimum effective depth to be provided for a continuous beam of span 13 meters in order to satisfy the vertical deflection limits as per clause 23.2 of IS 456/2000. Okay, so kindly refer to this clause and let me know what would be the correct answer. Pertaining to a continuous beam.
Answer D, 650.
Yeah, thank you for the response. Yeah, so I think we can go ahead with the solution, because we have a number of problems for today. So yes, it is option D is the right answer, definitely. So as per clause 23.2 of IS 456, so for beams which are having spans up to 10 meter, this has to be the the following L by D ratio criteria has to be met. Okay, so for continuous it is 26, but for spans which are greater than 10 meters, so the values provided in this particular clause 23.21a have to be multiplied by 10 divided by the span. Okay, so we'll just plug that. So for a normal case, when span is less than 10 meters, it has to be 26. On the other hand, it would be 26 multiplied by 10 by 13. Okay, so the L by D ratio has to satisfy this condition. Okay, we just simplify and we get this value. So when we simply rearrange the terms over here, so this effective depth D becomes L by 20, right? So that is 13 into 10 to the power 3 by 20. So this will give us a value of 650 millimeter. Okay, so even in the examination also, like you can expect these kind of very small but trick questions. So you have to be quite thorough with the concepts and the provisions of the code, so that you can directly refer and arrive at the correct answer. Okay. So moving on, so we move on to the a big problem on the deflection calculations. So a simply supported RC beam with dimensions of 300 mm by 500 mm and which is having a span of 5 meters carries a uniformly distributed service load of 30 kN per meter, and it is made of M20 concrete and 4 bars of Fe500 Fe415 which are of 20 mm diameter and are placed at an effective core of 50 millimeter on the tension side. So as a first part of this deflection calculation, we need to determine the depth of the neutral axis. Okay, so kindly use the working stress method and let me know what would be the answer. So please take 2 minutes and let me know what would be the correct answer. So anybody is able to get the answer? So I'll just explain. So here I have just drawn the cross section of the beam. It is having a width of 300 millimeter and overall depth is 500 and the effective depth is 450, and the beam is reinforced on the tension side with 4 bars of 20 mm diameter. So based on the working stress method, we need to determine the depth of the neutral axis. So we are going to assume the neutral axis at a depth of x from the compression fiber, and we are going to take the moment of the concrete area and the steel area, and the steel area is essentially determined by m into AST, where m is the modular ratio. M is the ratio of the modulus of steel to the modulus of concrete. So we get that as 8.94, and when you plug it all in this particular equation, we have b into x. So it is essentially developed from this diagram. So right, so b into x by 2 is equal to m into AST into d minus x. So we get a quadratic equation, so we need to use the scientific calculator, and we will get the value of 149.95. Okay, so if there is any doubt, please let me know. If there is any step that you have not you're not getting.
This last calculation, if scientific calculator is not there, we cannot do it.
No sir, like you need to have a scientific calculator because it's a quadratic equation. Actually you can do using this like you might be knowing that
Excel formula.
yeah, no, Excel is not required sir. Like you know that for a quadratic equation, you know that the
Sir, D 159.95.
no, like I am getting the value of 149.95. So
Okay.
yeah, kindly check that. So if you have a quadratic equation that is of this form, ax square plus bx plus c is equal to 0. So we have the roots of the equation. Let us call it as r1 and r2. r1 and r2 are given by minus b plus or minus root of b square minus 4ac by 2a. So if you are able to reduce this equation to this quadratic form, then we can obtain these values. So yes, so I request the participants to just verify, cross check the values that are that they are entering, and
Can you explain please on scientific calculator?
yeah, yes sir, definitely. I mean in the exam it should be allowed.
I am not getting it.
No, like you will be allowed to take scientific calci to your exam.
Yes, sir, in scientific calculator also I am unable to do. That is why I am asking.
Okay, sir, you can just you can search in YouTube maybe how to solve a quadratic equation on scientific calci. So you will get,
Okay. Thank you.
yeah. Thanks for asking, because I know some people, even we don't know what are the full functions of scientific calci. So yeah, so with that we can move to the next step of this deflection calculation. So for the beam given in question 3, we have to calculate the effective moment of inertia as per annexure C and compare it with the moment of inertia of the cracked section. Okay, kindly take 2 minutes and let me know what would be the right answer.
The effective depth will take 50 mm.
Yes, yeah. So the participants can just plug in the values and calculate the value of ICR, that is the crack moment of inertia. So I will just
13.49.
yeah, thank you, thanks for the response.
The moment we to take WL square by 24.
Moment, yes sir, yeah, you have to take, but the crack moment of inertia, you have to, it is quite different. So I'm going to proceed to the next slide to calculate the effective moment of inertia, right? So yes, so here we have as per the IS code, the effective moment of inertia, that is I effective, is equal to ICR. So actually the participants can still go ahead and calculate the I effective, and you can let me know what is the right answer. That's MCR by M into Z by T. So we have FCR is the modulus of rupture, that is 0.7 into root 20, which gives us a value of 3.13 MPa, right? So using the bending equation, we have MCR M by I. So this has to be the gross moment of inertia. M by I is equal to F by Y, FCR by YT. So this we are doing in order to obtain the value of cracked moment. So IGR,
Then what is YT?
YT is the overall depth divided by 2. Yes, so it is 500 by 2. So we have the gross moment of inertia. Let me just calculate here. IGR is equal to BD cube by 12, that is 300 into 500 cube by 12, that is 3125. Yeah, 3125 into 10 to the power 6 millimeter power 4, right? And we have YT is nothing but capital D divided by 2, that is 250 mm, right? So we have MCR is equal to IGR 3125 into 10 to the power 6 multiplied by FCR, that is 3.13 divided by 250. So this gives us a cracking moment of 39.125 kilonewton meter. Okay, so this would be the cracking moment for us. Now let us go ahead and calculate the remaining terms. So M, it is a simply supported beam. I am going to draw a small sketch over here. So it is for having a span of 5 meters, right, UDL, and it supports a service moment of 30 kilonewton per meter. So this would be the service load. So the service moment is given by WL square by 8. So this gives me a value of 93.75 kilonewton meter. Okay, right? So we have the value of ICR, MCR, M, and what does Z represent here? So the lever arm Z is, I'll take a different ink. So here Z represents the lever arm, that is the distance between the effective resultant compressive force and the tensile force, and Z is given by D minus X by 3, right? So if we substitute X as 149.95, I am getting a value of Z is equal to 400.02 millimeter. Okay, then we know the rest of the values. So let me just go ahead and substitute all the values in the expression for I effective is equal to, what was ICR? ICR was 13 point. One,
13.49.
yeah, thank you. 1348.59 into 10 to the power 6 divided by 1.2 minus 39.125 by 93.75 into Z by D 400.02. If my handwriting is not legible, please let me know so that I will try to write it more clearly. So 1 minus x value is 149.95 divided by 450. So for this I am getting a value of
10.16.
sorry
14.16 it is correct.
yeah, thank you. So 14.16 into 10 to the power 8 millimeter. Okay, so thank you for your response, and this is the right answer. Option E is the right answer. I effective is whenever there is one more clause in the deflection calculation, and that is, so whenever we calculate the effective moment of inertia, it has to fulfill this particular criteria, that is cracked moment of inertia, it has to be less than the effective moment of inertia, it has to be less than the gross moment of inertia. So even if we get I effective as lower than the crack moment of inertia, we need to consider the ICR value only. Okay, so we need to ensure that this particular criteria is being satisfied. So option E was the right answer. So I hope that I'm not going too fast. If not, we can move ahead with the next problem. Okay, so once you have got the effective moment of inertia, we need to determine the short-term deflection at the midspan of the beam using the expression based on elastic theory. So this is quite straightforward. So kindly take 1 minute and let me know what is the right answer. I'll write the equation also for your convenience. So for a simply supported beam subjected to UDL, what is the equation for the maximum deflection? Okay, I'm sure that you're all familiar with this equation. So let me just plug the values. Okay, kindly let me know what is the delta S, delta short term deflection due to the loading.
$18.49.
You mean 18, sir? 18?
This came very high, this.
No. Kindly check once again. It cannot be. So 5000 power 4 by 22360.
But actually, one more formula is there, sir. ML square by 4 EC I effective.
Yes, sir. That is also there.
Both are same.
Yeah, both are the same. So what we do is we convert the moment into the UDL into moment. That's all. So both are the same. So we can actually you can actually check I think later. So I'm getting a value of 7.7 millimeter. You can actually do that using the moment also actually. So sorry. So we have moment is equal to WL square by 8, right? So this would be 5 by 384 into WL square.
This effective ML we will not take.
No. We have to take this effective I and EC, and M value has to be 93.75. This M value. Okay. So this can be so this can be 5 by 48, right? 34. So this can be 48 into 1 by this is L square by EC I effective, or it can be, this becomes M, so this would be 5M L square by 48 EC I effective. So we can just plug in and see what we are getting here also.
That is 4 EC, sir. 4 EC it is.
No.
The
No, 40.
notes it is given 4 EC.
No, sir. It is not like that. Yeah, so in this also I'm getting the same answer, 7.7 millimeter. Okay. So this is I mean that was for a cantilever beam. Hello.
Okay, sir.
Yes sir, so that was for a cantilever beam and this is for a simply supported. Okay, so
Okay.
yeah,
Thank you.
so 7.7 is the right answer. So moving on, so this is the short term deflection corresponding to the loading. Then here we are going to determine the deflection due to shrinkage. Okay, kindly take 2 minutes and let me know what would be the right answer.
How to take this K3 and K4, sir?
You have to refer to the annexure, this one. So if it is given actually. Yes. So for a simply supported beam, K3 is 0.125 and K4 is given here. So here PC is 0. Compression steel we are considering 0. And here again K3 is 0.125 and K4, as we can see here, it is depends on the value of PT minus PC. So PT minus PC is whenever the PT minus PC value is between the range of 0.25 and 1.0, we have 0.72 multiplied by PT minus PC under square root of PT. So PC is 0, so this simply becomes 0.72 root PT. Okay, so PT is 100 AST by BD, and when we simplify this term K4, so 0.72 under root 0.93, right? So K4 turns out to be 0.695, right? So we will plug in all the values in this delta SH. Delta SH is equal to 0.125 into 0.695 into epsilon CS. If it is not specified, it can be taken as 0.0003, and it is based on the clause 6.2.4 of IS 456, and L is 5000 square by 500. So when we simplify, we get a value of delta SH as 1.30 millimeter. It is quite straightforward. So option A is the right answer. So I hope we can move on. Yeah. So for the same beam, assuming that 70% of the moment is due to permanent load and the age of concrete at loading is 28 days, determine the deflection due to creep as per the annexure C of IS 456. Okay, I will start solving the problem. Even I request the participants also to start solving. Okay. So essentially here also the procedure is somewhat similar. So in order to obtain the deflection due to creep, we need to calculate the deflection due to the loading plus creep. Then you have to subtract it by the deflection due to loading. And whenever we are calculating the value of delta, so this has to be corresponding to the modified modulus of elasticity of concrete because of the creep effect. So I'm just going to start with the calculations. I'm going to take a different ink for contrast. So we need to locate the neutral axis. Okay. So we are going to perform the same mathematical operations in order to locate the depth of neutral axis, considering the effect of creep and the modified properties of concrete, that is bx square by 2 is equal to m into ast into d minus x. So upon substituting, I will substitute the values, that is 300 into x by 2 is equal to m 23.26 into 1256.64 into 450 minus x. So this gives us a value of 214.3 millimeter. 214.3 millimeter. Okay, so I'm going to go ahead to the next page of the calculations. So what do we do after locating the neutral axis? We're going to find out the lever arm. So lever arm, that is z is equal to d minus x by 3 as per the working stress method and triangular distribution of stress distribution of concrete. So that gives me a value of 378.56 millimeter. Then we'll find out the crack moment of inertia, ICR, is equal to bx cube by 3 plus m into ast into d minus x whole square. Okay, I'm going to substitute, and 300 into x value is 214.3 cube by 3 plus m is 23.26 1256.64 into what is d, 450 minus x is 214.3 whole square. So we get a value of ICR as how much?
26.20, right?
Yeah,
Okay.
yes, thank you. 26.076 into 10 to the power 8 millimeter power 4. Okay, and similarly we'll find out the value of I effective also. Okay, it's a lengthy problem. I will try to use this space as well. Okay, and MCR we got previously was, yeah, so let me substitute the value here. So MCR M by ICR is equal to M by I is equal to FCR by YT. Okay. So this has to be not ICR, it has to be IGR, gross moment of inertia. Okay, so this is similar to our previous problem. So here also we will get MCR is equal to 39.125. So there is no difference from the previous case for the short term loading. So I'll go back and just show it to you. So here also we got 39.125. So in the calculation of deflection under creep also, the value of MCR would be 39.125. Okay, so after that, so this comes, here comes the most important part for the creep calculation. I'll take a different color. So we are considering that the age of concrete is 28 days, and we will take that the moment due to permanent loads as 70%. Okay, 70% of the total moment will be taken as due to permanent loads. Due to permanent load. Okay, so that would be M is equal to 0.7 multiplied by 93.75. So M, we will get a value of 65.625. Okay, so which is why, you know, I have specified this number in the question also, that we should consider 70%. If the number is not given, then it is a practice to consider 70% value. Okay, so we will use this value in order to find out the value of effective moment of inertia. So that is I effective. I effective will be ICR, right? ICR divided by 1.2 minus MCR by M into Z by D into 1 minus X by D. Okay, so here we need to substitute ICR from this this value, and M has to be this particular value. From that I am obtaining the value of I effective as do we have a empty slide? Yes, we have an empty slide. So I effective is 27.82 into 10 to the power 8 millimeter power 4. Okay, so we are going to use this I effective for our delta I plus CP and delta I calculations. Okay, I hope you're able to understand, you're able to follow the calculations along with me, right? Right, so we will first calculate delta I plus Cp. Okay, delta I plus Cp and delta I. Okay, so I will calculate it side by side. So that is given by 5 by 384 into WL power 4 divided by ECE I effective. Okay, and delta I is given by 5 by 384 into WL power 4 divided by EC into I effective. Okay, so this is the difference. Here we are going to use ECE, that is modified modulus due to creep, and here it would be the original, and this particular delta I would be corresponding to 70% of the service moment. Okay, so I'll substitute so that you can verify. Into 30 into 5000. So this is basically about the procedure. Like once you're able to familiarize yourself with the procedure, it becomes very simple actually. Okay, that is ECE, and I effective is 2782 into 10 to the power 6, right? And here side by side I'll calculate delta I 5 by 384 into 30 into 5000 raised to the power 4 divided by, what is the value of EC here? EC is 22360.7 into I effective is, we'll use that value 2782 into 10 to the power 6. So we get this value as 10.204 mm and delta I, and we get a value of how much? 3.925 mm. So here delta Cp is given by delta I plus Cp minus delta I, which gives us a value of 6.28 millimeter. Okay, so it is about basically about practice and knowing which term comes, how to use the different terms used for the deflection calculation. Okay, so I hope that the procedure is clear to some extent.
Right, effective we got 27.82 na sir. That we have to use actually.
Yeah. So that was 27.82 into 10 to the power 8. So it's just expressed as into 10 to the power 6. So I use this for my calculation. So it is one and the same.
So in delta I we have to use 2272360.
Yeah. So this is without
Okay.
considering the creep effect. So, but this is considering the effect of creep.
Okay, thank you.
Yeah, thank you. Yeah, so ultimately we obtain the deflection due to creep as 6.28 millimeter. So option C is the right answer. Okay. So there is one more subsection. So here essentially we need to check whether the beam satisfies the clause 23.2a and 23.2b. So here the correct answer is option A. So the option A, actually the overall deflection, it has to be less than L by 250, and this has to be less than L by 350. Okay, so I will just
12.55.
yeah, so I will just quickly discuss here. So it has to be 20 millimeter, that's the upper limit, means it should not go beyond this, and here it
14.28.
yeah, thank you. 14.29 I'm getting. Right. So in the first case, the total deflection, so I'm going to separate these out. Okay, I'll take different inks, actually that would be better. So I'll take here, so the total deflection is delta T is equal to delta short term plus delta shrinkage plus delta Cp. Okay, so I'm getting a delta T value of 15.3 millimeter. So this is less than L by 250, which goes to say that the 23.2A is satisfied. So it is satisfied. And how do you calculate for this? So this is including the effects of temperature creep. So it is usually after a period of time, for example T is equal to 28 days, and we are going to consider that the loading, the moment would be 0.7 times the actual moment. Okay, so I am going to call this as M dash. Okay, so for that again here delta T is equal to, I'm going to write it as delta S prime, delta S prime plus delta SH plus delta C. So here I'm getting delta T as 11.505. Okay, just for clarity, I'm going to write down what is the delta S and delta S prime values that I substituted. So for this case, delta S is from this question number 5, that is 7.7 millimeter. Okay, this would be 7.7 millimeter. Okay, and here delta S dash, this would be from this question number 7, where we considered these 70% of the moment. Corresponding to this calculation, we get 3.925. Okay, so this would be 3.9 millimeter. Okay, so which is why we are able to satisfy both the criteria. So option A is the right answer. Okay, so we'll move very quickly to the next question. So we are going to move on to the calculation of crack width. Okay, so it is required to calculate the depth of neutral axis and the crack moment of inertia for this particular beam cross section. Okay, kindly take 2 minutes and let me know what would be the right answer. So here I think one particular data is missing, so here it has to be M25 concrete. So M25 concrete and Fe 500 steel. Fe 500. So I will start with the calculations. Right. So we have, I'm going to use this area only. So we have this diagram B, we have X, right, and here we can consider the equivalent area of steel, that is M into AST. So how will you, what is the equation for location of neutral axis? So we have the location of neutral axis, that is bx square by 2 is equal to M into AST d minus x. So I'm going to just substitute here 300 x square by 2 and these bars are of 20 mm diameter. Okay, I should have included that. Sorry, these bars are of 20 mm diameter. Okay. So the modular ratio is given by ES by EC, that is 2 into 10 to the power 5 by EC is 5000 into square root of 25. So we get a value of 8. Okay, 8 into, what is the value of AST? I'm going to calculate here.
942.85.
Okay, thank you. So we have pi by 4 into 20 square multiplied by 3. So we have 942.8. I'm considering it as 942.5 millimeter square. Anyway, moving on. 942.5 into d minus x. So d is, we'll take an, we have to assume effective core of 50 millimeter. Sorry for that, I should have mentioned it earlier. So we can take it as 50. Okay, and we have 450 minus x. So once we substitute all these, we will get the value of x, or the depth of neutral axis, as x is equal to how much? 127.35 millimeter. Okay, so let us calculate the cracked moment of inertia. So ICR is given by based on the working stress method, bx cube by 3 plus m into AST into d minus x whole square. Okay, let us substitute the values. 300 into x value is 127.35, 127.35 whole cube by 3 plus 8 into 942.5 into 450 minus 127.35 whole square. So upon simplifying, we get the value of ICR as 991.5 into 10 to the power 6. So we are going to use the value of ICR in our crack width calculations. Okay. So the correct answer is option D, and our ultimate goal of solving this problem is that we need to calculate the crack width corresponding to these 3 points, that is A, which is at the corner, and B, which is vertically exactly, that is vertically below this in the extreme tension fiber, and this point C, which is located as at a depth of 2 by 3 into d minus x from the neutral axis. Okay, so in this particular question we have determined the location of neutral axis and we have determined the crack moment of inertia. So we will see the next part of the question. So for the beam given in question 9, we have to determine the mean strain at the level considered for the points A, B and C. Okay, so we need to take the help of the IS code, and we need to I'll go to the annexure F of IS 456 and we need to determine the value of epsilon m. Determine the value of epsilon m for points A or B and C. Here A and B are going to be same because they are at the same height. Okay, kindly take 2 minutes and let me know what would be the right answer. Okay. Right, so for that we need to first draw the cross section and the strain distribution in the beam. So I'll be solving with you. You can just take my help and we can solve the problem together. So this is the cross section and it has 3 bars of 20 millimeter diameter. The width is 300 millimeter and effective depth is 450, right? So we have 3 of 25, and we will mark the value of neutral axis here. Neutral axis depth, that was 127.35, 127.35, and let me mark the points here. We need to find out the crack width corresponding to 3 points, that is A, B, that is vertically below this, A, B and C. So here we have we need to write down the value of d minus x, right? So I'll write it down. This would be 450 minus how much would that value be? So the total depth is 322.65, 22.65, and I will mark the distance corresponding to point C also here. So we have point C, and point C is 2/3 of the value of d minus x, which gives us a value of 215 millimeter, 215.1. We'll be using it later in our calculations, so I will move ahead with the calculations for now. Right. Yeah, so we were marking the strain distribution along the depth of the cross section. Okay, so we need to find out the strain corresponding to the steel. Okay, so we have strain corresponding to this steel reinforcement. Okay, we need to determine this strain at this point, so that is given by epsilon CS. Okay, okay, yeah, sorry for that delay. We'll proceed with the calculations. Right, we have x, we have d minus x. Now we need to find out here epsilon CS corresponds to the strain in concrete at the level of steel. Okay, so that is given by F into CS by EC. Okay, so how do we find out the value of stress? It comes from the bending equation, that is M by I is equal to F by Y, or FCS would be M by I into Y. Okay, so this is the stress within concrete corresponding to the level of steel. Okay, So how do we find out the value of M? I'm going to write down the calculations on the side so that it is given that it's a simply supported beam over a span of 6 meters subjected to UDL of 15 kN per meter. Okay, so we have M is equal to WL square by 8, WL square by 8, that is 15 into 6 square by 8. Okay, I'm going to just calculate that. That is
67.5.
Yeah, 67.5 kilonewton meter. Okay, and we have found out the value of ICR, so I'm going to write it as ICR, and Y is nothing but this D minus X. So this Y is the distance from the neutral axis. Okay, so I'm going to substitute the value. FCS is equal to 67.5 into 10 to the power 6 into D minus X. So D minus X is 322.65 divided by, what was the value of ICR? 991.5. Okay, yeah, 991.5 into 10 to the power 6. So we get the value of FCS as how much? 22.0 MPa. Sorry, I'll just write it once again. Okay, so we need to find out the value of epsilon m, which is why we are doing all these calculations. So FCS is 22.0 MPa. Now we have the value of epsilon CS as FCS by EC, that is 22.0 divided by, so it is, since it is 25 MPa, it simply becomes 25,000 MPa. So we have the value of epsilon CS as 0.00088. So this is the strain in concrete corresponding to the level of steel. Okay, so from this we need to determine what is the strain at the level considered. Okay, so we need to take the help of the diagram here. Okay, so okay, let me just, so here we need to find out the value of epsilon 1. Okay, so epsilon 1 is nothing but the strain at the level considered. Okay, so yeah, just follow me, just stay with me so that we can do the calculations together. So here is the strain distribution diagram. Now we have found out what is the strain corresponding to this point. Okay, and here I will write down the numbers also. Oh, I'm sorry. I'm going to write down the numbers so that we can visually understand how we are performing all the calculations. Okay, so we know the strain corresponding to this point. and what is the distance here? 322.65. And what is this? This becomes, add the effective cover, this becomes 372.65. okay, and this particular value, this is corresponding to the points A and B. Okay, and this one more value, I'm going to write it by a dot, corresponds to the point C. Okay, and this would be 2 by 3 of 322.65. okay, 2 by 3 of 322.65. okay, so here we will find out the value of epsilon 1. Epsilon 1 corresponding to the points A comma B is how much? 0.00088 into 372.65 divided by 322.65. okay, so this will give us the value of epsilon 1, that is 0.001. okay, so this we are going to be using in this equation to obtain epsilon m, and correspondingly this mean strain, average steel strain, we're going to be using to determine the crack width. okay, so this is corresponding to points A and B. Then we need to find out the epsilon 1 corresponding to point C. So this would be simply 2 by 3 of the strain corresponding to this value, that is 0.00088, which gives us a value of how much? 5.87 into 10 to the power minus 4. 10 to the power minus 4. okay, so once we have obtained here, we need to determine the value of mean strain. okay, so yes, so here we have to find out the value of mean strains. okay, so we will just substitute the values here. So for corresponding to points A and B, okay, I'm going to just write down what are the corresponding terms, and here see what are the corresponding terms. So H is the overall depth of the cross section, X is the depth of neutral axis, A here corresponds to the distance from the compression phase to the point at which the crack width is being calculated. okay, so and here ES is the modulus of elasticity of steel, and AS is the area of tension reinforcement, and D here is the effective depth. So I'm going to just quickly write down all the values. okay, so epsilon m is equal to epsilon 1 is 0.00088. I'm sorry, it has to be 0.001. So 0.001 minus H is 500 minus X is 127.35 divided by 500 minus 127.35 divided by 3 into ES is 2 into 10 to the power 5 and AS is 942.5 into D minus X is 450 minus 127.35. okay, so this is corresponding to the points A and B, for which I get a value of epsilon m, is equal to how much? 7.72 into 10 to the power minus 4. Okay, and for epsilon c, by substituting the value of a here, only the value of a changes, and for c I'm going to use a different color for better understanding. So for c, a, the value of a would be 342.45 millimeter. Okay, so this I got from, this would be x plus 2/3 of d minus x. Correspondingly, we'll get the value of epsilon m as 4.55 into 10 to the power minus 4. Okay, so here option C is the right answer, because 7.7 and 4.6 into 10 to the power minus 4. Okay, so once we have found out the value of epsilon m, the next step is to determine the crack width. Okay, so I hope that you're able to follow the problem until now. So you can just note down these values for epsilon m. Epsilon m for A and B is 7.72 into 10 raised to the power minus 4, and epsilon m for C is 4.55 into 10 raised to the power minus 4, and we can go ahead and calculate the crack width corresponding to these values of epsilon m for the points A, B and C. Okay. So we have, I am going to start writing the equation here. WCR, that is the crack width, is 3 times ACR into epsilon m divided by 1 plus 2 times ACR minus C minimum divided by H minus X. So what does each term mean? We'll go to the highest code. So here ACR corresponds to the distance from the point considered to the surface of the nearest longitudinal bar, and C minimum corresponds to the minimum cover to the longitudinal bar. Right, so we will take C minimum as 40 millimeter. Okay, we will take C minimum as 40. Now we have the value of epsilon m, we know for all the points. We know the value of H, we know the value of X, we know the value of C minimum. We need to only find out the value of ACR. So what is basically this ACR? So ACR is essentially the distance between the point considered to the surface of the nearest longitudinal bar. Okay, so we will calculate that ACR now for the different points. Discontinuity. Different color now. So basically we need to, ACR is basically from this point to the surface of the longitudinal bar. Okay, so we can find out the value for ACR calculation. Okay, I'm going to divide it into 3 boxes for A, B and C. Oh, sorry. So this I'm going to consider for point A and point C, and point B is quite straightforward because here we know that the effective depth is 50 millimeter and the dia of the bar is 20 millimeter, so that is 50 minus 10 or 20 by 2. Okay, so ACR for point B is 40 millimeter. Okay, and here we have to find out ACR for point A. So let us go back and take the help of this. So it is 50 millimeter from here. So here it is 50 millimeter. So here ACR is given by square root of 50 square plus 50 square, okay, under root minus 10. Okay, so minus 10 is not included in the root, so I am getting ACR corresponding to point A as how much? 60.7 millimeter. And here ACR corresponding to point C, right? So this particular height is 1 by 3 of x, okay, or it is x by 3, sorry, it is d minus x by 3, d minus x by 3, which is equal to 107.55. Okay, so here it is nothing but square root of 50 square plus 107.55 square minus 10. Okay, I am getting ACR corresponding to point C as 108.6 mm. Okay, I'm just going to box it. Okay, so when we consider the ACR values for different points, okay, so when we substitute the different values, so I'm just going to do it for the point A. Okay, so when we consider WCR corresponding to point A, we have 3 times, what is the value of ACR that we got? 60.7 60.7 into epsilon m. What is epsilon m? Epsilon m is
7.7.
Yeah, thank you. 7.7 into 10 to the power 4 minus 4, sorry, divided by 1 plus 2 times ACR is again 60.7 minus C minimum is 40 millimeter divided by h. H is overall depth 500 minus, is it 127? Yes, it is 127.35. So I am getting a value of WCR for A is 0.127 millimeter. Similarly, I am going to write for the remaining 2 points also, which you can verify later on. WCR for B. So what is the purpose of this crack width calculation? So after we have done the after we fulfill the limit state of collapse, we will calculate for the limit state of serviceability. And if it is concerning, like for very severe environmental exposure conditions, so it is given that it should not exceed 0.2 millimeter. So then we can take the corrective steps by adding more reinforcement or similar steps. 0.093 millimeter, and this is 0.108 millimeter. So here point A is the most critical one, but here also the crack width seems okay. Okay, so here point option A is the right answer. Okay, so we have exceeded the time, so I would like to take another 10 minutes extra in order to discuss this development length problem. Okay, so yes, kindly bear with me for another 10 minutes. So for the cantilever beam that is shown below, that is subjected to a total factored load of 100 kilonewton, determine the development length required for the tension and the compression steel, and let me know whether the provided lengths are adequate or not. Okay, so we can start the problem. Okay, we can solve the problem together. And so LD, I'll start with tension. Okay, is equal to, and LD for compression is equal to, so right, and please note that this is the cross section. So based on the codal provisions, we have LD is sigma s into phi by 4 into tau BD. Okay, this is the bond strength, and this can be increased by 60% if we are using the deform bias in tension. Okay, so sigma s, we are going to consider the maximum allowable tensile stress. Okay, so this is quite straightforward. I hope you'll be able to understand and calculate the answers along with me. So we will take the tension steel. So tension steel is 25 dia, 25, right, divided by 4 into corresponding to M20. What is the value of tau BD? And for compression we have sigma s, same equation, but in addition to that we need to consider 25% increase for the rebars which are provided in the compression zone. Okay, so we have 0.87 into 415 into we are providing 16 dia bars. Okay, 16 divided by 4 into 1.2 into 1.6 multiplied by 1.25, because for compression we are increasing the bond strength by 25% in addition to the 60% considered for the deformed bars. Okay, so kindly calculate and let me know what are the correct answers. Okay, okay, so I hope you are able to obtain the same answers. So the required development length in the tension zone at the top, that is 1175 millimeter, and in the compression zone it has to be 602 millimeter. So option A is the right answer. Okay, so do we have the okay, so we will just check how much is the actual development length that is being provided and whether we need to make some modifications to that. So we have LD provided in the tension zone, and we have LD provided in the compression zone. Okay, so in the tension zone it is quite simple. We have 280, and for a 90-degree bend we have 8 into the diameter. Okay, right, we have 8 into 25. We consider that value for a 90-degree hook, and plus 300. So how much do we have? And here in the compression we have just 300 millimeter.
Question 780.
Yeah, it has to be 780. Okay, so definitely here we are short of the development length that is required. Okay, so we will go ahead to the next part of the problem. So how we are going to meet the required development length criteria as per the IS code. Okay, so this is as per clause 26.21. we have the expression for the development length, and here as one of the participants you were asking, so here we are considering the ultimate load. So bond the development criteria, the development length criteria comes under the limit state of collapse, but the crack width calculation and the calculation of deflection, that comes under the limit state of serviceability. Okay, so and then the tau BD value, that is the design bond stress, so that is comes under this particular clause. Okay, so yeah, so for the cantilever beam, so we need to determine the anchorage length based on the area of steel that is required. Okay, so I'm just going to give the values so that we can perform the calculations straight away, right? So I have considered this cantilever beam, right? So which is having a span of 2 meters, and it is given that the factored load is 100 kilonewton. So this is the total load. Okay, so this comes out to be 50 kN per meter. Okay, so I'm just going to draw this 50 kN per meter, and for the cross section, that is 200 by is the overall depth. Have they not mentioned it? It has to be 400. I think somehow that yeah, here it is. So for this cantilever beam having a cross section of 200 millimeter width and 400 millimeter depth, so I used as per the IS code, I calculated the area of steel that is required and area of steel in the compression region and in the tension region. So based on the moment requirement, right, so for this particular I'm going to use a different color. Okay, kindly bear with me, we will try to understand this problem. And so mu is given by WL square by 2, right, for a cantilever beam, that is 50 into 2 square by 2. So mu is 100 kilonewton meter. So we have the value of mu over here, and for this cross section, for this cross sectional dimensions, I was finding out that the limiting moment of resistance is,
Sir, UDL is 100, na? 100 into 2 square root.
no, this is the total load, sir. This one is the total load, so it has to be 50 kilonewton per meter. So that is why
Okay.
in the question also it is total factored load.
Yeah, in fact.
Yeah. So we have the limiting moment of resistance as 71.52 kilonewton meter. So we have to design it as a doubly reinforced cross section. Okay, so using the SP16, right, so I found out that the AST required and ASC required, and ASC required are how much? 934 mm square and 261 mm square. Okay, so please note that I'll take a different color once again. So here the AST required is 934 and 261, but how much is the actual AST and AEC that we have provided? So that is comparatively on a higher side. Okay, so AST provided is pi by 4 into 25 square into 2, and ASC provided is pi by 4 into 16 square into 2. Okay, so this was excuse me, yeah, so this was the actual okay. So this turns out to be how much? I am getting a value of 981.75 mm square, and here for compression I am getting a value of 390, no, sorry, it is 402.12. So this is the AST provided, this is the required AST, provided AST, required ASC, and the provided ASC. Okay, so now the development length can be calculated by this the actual development length required. Okay, LD required can be LD that was previously calculated multiplied by AST required by AST provided. So for tension, this would be for tension and this would be for compression. Okay, for tension I'll use this color only. So that would be 1175.3 into 934 divided by 981.75. okay, so this is what we are doing, 934 and 981. So correspondingly we can say that it can so this much of development length is sufficient. And for the compression again we have 602 multiplied by 261, that is AST that is actually required, divided by the ASC that is actually provided. Okay, so here we have 390.7 millimeter. So here you can see that, so 1118 and 390. So if we consider the actual area of steel that is required instead of considering the AST that is provided, then the development length requirement drastically reduces. Okay, so I hope that you are able to understand what we are doing here. So here essentially it is corresponding to the area of steel that is required, and in the earlier question, that is question 12, it was corresponding to the area of steel that is provided. Okay, so if the area of development length is slightly more than what is being provided, there is scope for justifying that the AST required if it is slightly less than the provided, so we can actually go ahead with the provided steel. But in our case actually the difference is quite substantial. Okay, so here the compression it is 300 millimeter, and the tension area, again the difference is more than 300 millimeter, so we have to go for some kind of a modification. Okay, further, so if we are providing instead of 25 mm bars, if we are providing 20 millimeter in the tension region, and if we are providing instead of 16 mm bars, if we are providing 12 mm in the compression region, what would be the modified development length to be provided? Okay, kindly take 1 minute and let me know. We have already solved it for 25 mm dia and 16 mm dia. Okay, into 5, that is 20, divided by 4 into 1.2 into 1.6, and we have LD is equal to 0.87 to 415 into 12 by 4 into 1.2 1.6 to 5. Okay, so color, take red. So this corresponds to the development length in the tension region, this corresponds to the compression region, and when we modify, actually, so we can actually meet the same area of steel requirement using the lesser diameter bars. Okay. So this would be 200 millimeter, okay, and this would be 400 millimeter, and then instead of we can provide 3 bars of 20 mm diameter and 3 bars of 12 mm diameter, and still we can meet the criteria. Okay, so that is the point, because when you reduce the diameter of the longitudinal bars, the requirement of development length automatically comes down, because the development length requirement is directly proportional to the diameter of the longitudinal bar. So we can actually, by providing lesser number of bars of higher diameter, instead of that, if we provide more number of bars of lesser diameter, we can actually meet the development length criteria. Okay, so when you go for this, how much does this come out to be? Can you please calculate and let me know? We will wind up in another 5 minutes, so I am getting a value of 940 millimeter. And for the compression region, I am getting a value of multiplied by 12. Yes, I am getting a value of 451.3 millimeter. So it drastically reduces. So the correct answer is option B. Okay, so here we can see that how in comparison to the 25 mm diameter bars, I will just write down the values here. How it compares to the earlier configuration. So when we are providing 2 of 25 5, so the LD required was how much? Yeah, it was 1175 millimeter. So we can reduce the development length required by more than 200 millimeter, and here when we had provided 2 of 16 mm, the requirement was 602 millimeter. Okay, so basically by providing this we can substantially reduce it. So I'm going to draw a table very quickly here. So we have the required LD and the provided LD, and we have the modifications. And here corresponding to the tension steel and the compression steel. Okay, tension and the compression. Okay. Okay, so let us see how we can address the problem. Now the required LD was 940 millimeter based on our calculation. Okay, 940, and in the compression it was 451. Let us make it 452. Okay, all of them are in millimeter. So this would be 280 plus 90-degree bend, that is 8 into 20 plus 300 is equal to 740, and here it is 300 millimeter. So the solution is, you have to extend it by another 200 millimeter, and here we need to extend it by another 150 millimeter. Okay. Or you can provide a 90-degree bend. Okay, so the solution is, you reduce the diameter of the longitudinal bar, and then you're going to provide the extra development length of, you will extend it even further by 200 millimeter, and you're going to take this and take a 90-degree bend and anchor it in the upward direction. Okay, so we come to the last question now. So it's the conceptual one. So which of the following steps can be taken if the development length provided for the reinforcing steel is inadequate? So there are multiple options, so kindly let me know what would be the correct options. Do we increase the dia of longitudinal steel, or do we provide hooks, standard hooks, decrease the grade of steel, increase the grade of concrete? So I think there are four. There are 4 correct options, I think. There is one incorrect option.
D and E.
Okay, okay, thank you for the response. So we can go ahead with the answer, I think. So here even option C is also viable. So because if you reduce the grade of steel, let's say that you're providing 500. Initially you have provided 500, and if you're able to satisfy the AST requirement with 415 also, so if you reduce the grade of steel, we'll reduce the development length requirement also. Okay.
Yeah. Okay.
Yeah, okay. Okay, I think with that, yeah. So if you take a 90-degree bend, so the equivalent anchorage length or the development length is 8.5, and here it is 16.5. With that, we will come to the conclusion of today's session. So thank you so much for joining tonight. So next week we'll be having the last final live interaction session. So the reason why I went ahead with with these big problems is that for your exam, question can come from any part of the syllabus. So I know that it was difficult for me also. It was, the problems were quite lengthy for weeks 9, 10, I'm sorry, 10, 11 and 12. It was quite lengthy, but I hope that our efforts will be fruitful, and you can attempt the exam in a better way. We can learn the concepts, and we can attempt in a better way. So if there is any comments, like we can discuss, or we can end the session for today.
All this material it is in NPTEL. Is it available every time, sir? Anytime? There is a cutoff.
You mean the videos, sir, or
Videos, notes, everything.
yeah.
Lectures.
The lectures will be there on YouTube. Like I can assure from my side that all the live interaction session, it will be on YouTube, and even NPTEL also, it will be available all the time. But if you want, you can download, and you can keep it for your personal use. And the lecture slides are anyway there in the form of PDF, so you can download, and you can keep it. So
Thank you.
thank you so much for joining, and we will meet again next week for the design of two-way slabs. Thank you.